All right, so we'll wait until some more people join before we get started with the session. All right, so it seems that people have stopped joining, so let's get started with the session. So welcome everyone to today's Logic Math Club session. Today we'll be going through some problems from the 2022 Exeter Math Club competition, and namely we're going to go over some problems from the team round. But before we go to the discussion session, I'll give you all some time to think about these problems. And so I'll give you all around 30 minutes before we move on to the discussion. All right, so now let me post the link to the problems in the chat. As mentioned earlier, we will talk about the odd numbered problems. And so let's start with problem 1. So for problem 1, we're asked to compute the sum of these numbers. So we have 1, 3, 6, 10, 15, 21, 28, 36, 45, 55. So one of the first things you can see about the sequence of numbers is that all of them are triangular numbers. Yeah, so one way you could go about this is you could try to basically pair up things that sum up to a multiple of 10. And so we get nice numbers that we can sum easily. So yeah, for example, what Yo-Yo is doing, we're combining 1, 3, and 6 into one group, which has some 10. We're combining 15 and 45 to another group, which has some 60. And then to complete this, we can notice that, yeah, go ahead. Yeah, the sum of those three give another multiple of 5. Yeah, so those three sum up to 85. And when you sum up 85 and 55, you get 140. So once we do all these smaller sums, we can add up these sums that we got. So there's 10, which comes from these three. We have another 10. And then we have 15 and 45, which makes 60. And lastly, we have these four, which make up 140. So at the end, our sum is just 10 plus 60 plus 85, or not 85, but okay, 10 plus 10 plus 60 plus 140. So this way, we can get the sum to be 220. So yeah, that is one simple way to do this problem. So another way to do this problem is by noticing that we have triangular numbers, we can write all of these numbers in as binomial coefficients. So we have 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus 5 choose 2, 6 choose 2, 7 choose 2, 8 choose 2, 9 choose 2, 10 choose 2, 11 choose 2. So all the way up until 11 choose 2. And here we can notice that we can apply hockey stick theorem or hockey stick identity to this sum of numbers, this sum of binomial coefficients. And namely, we can get that the sum is equal to 12 choose 3. And computing this, we get that this value is exactly 220. So those are two ways to go about this problem. One way is to use binomial coefficients, and the other is to pair up numbers to make adding more, basically adding things easier. So the answer is 220, and that's problem 1. Any questions? Okay, so I haven't gotten any questions, so let's move on to problem 3. Okay, so in problem 3, we have points x and y that lie outside a regular pentagon A, B, C, D, E. And we're told that these points x and y satisfy the condition that ABX and DEY are both equilateral triangles. So let's draw a diagram for this. And I have this diagram drawn. And we want to find the angle measure of angle XZY, which is this angle right here that is marked in black. And as you can see, we have our regular pentagon ABCDE, as well as equilateral triangles ABX and DEY. So one thing you might think is, how do we find the measure of angles XCY? So one thing we can do is we can find a bigger angle. So we can find BCD first, and then subtract off these smaller portions. So we'll do exactly that. So first, since BCD is an internal angle of a regular pentagon, its angle measure is 108 degrees. And in case you don't know this, or we want to work with a larger polygon, like a heptagon, for example, generally the way to find the internal angle measure of a regular n-gon is by first noting that the total sum of all angles is exactly 180 degrees times n minus 2. And then since there are n angles, each angle has measure 180 degrees times n minus 2 all over n. And having a pentagon means this angle is equal to 108 degrees. So that's why angle BCD is equal to 108 degrees. And then once we've found angle BCD, we still have two other small angles over here that we want to find. And one thing we can notice is that these two small angles should be equal because the diagram is symmetric. The diagram is symmetric about this line. So it suffices to find one of these angles. So let's look at this angle, for example. So let's focus on this angle. So one thing we can note about this angle is that this angle is inside an isosceles triangle. And specifically, it's inside this isosceles triangle, YDC. We know this is isosceles because we have an equilateral triangle attached to an equilateral pentagon. And so all three of these lengths have equal length. And so what we can notice here is triangle YDC is isosceles. And so now that we know that triangle YDC is isosceles, in order to find angle measure YCD, this angle over here, we just need to find angle YGC, which is this larger angle. So let's find angle YDC. We notice that angle YDC is a combination of angle YDE, which is an internal angle of this equilateral triangle, and angle EDC, which is an internal angle of this equilateral or regular pentagon. So we have these two angles, this and this. We can write this as 60 degrees plus 108 degrees, which is 168 degrees. So the angle measure, the measure of angle YGC is 60 degrees from the equilateral triangle plus 108 degrees from the regular pentagon. So that angle measure is exactly 168 degrees. And so now we can find the measure of angle YCD. Since triangle YDC is isosceles, so the sum of the other two angles is going to be 180 minus 168, so 12 degrees. And then we divide by 2 since there are two other angles. And we find that YCD has measured 6 degrees. This is 6 degrees. And so lastly, we already know the measure of angle BCD and also the angle, the measure of angle YCD. And similarly, this is also 6 degrees. So the degree measure of XCY, which is what we're looking for, is 108 degrees minus 2 times 6 degrees, which gives us a final answer of 96 degrees. So that's our answer. So are there any questions? Okay. So I haven't gotten any questions, so let's move on to problem 5. All right, so in problem 5, we have 3 points, A, B, and C. So this should say A equals the point -20, 22, B equals the point K, 0, and C equals the point 202, 2, all in the coordinate plane. And we're told that if angle ABC is 90 degrees, we have some values of K that work. And we want to find the sum of all possible values of K. So let's think about this problem geometrically. We have a circle somewhere in the coordinate plane, or no, we have 2 points A and C somewhere in the coordinate plane. And we have a point B that's on the x-axis. So this is not drawn to scale. I'm just trying to illustrate here what the problem conditions really mean. So let's say B is here. Then we're told that the angle measure of ABC is 90 degrees. So what this means is that B is on the circle with diameter AC. So in fact, the possibilities for B, or the locus of B, such that they satisfy this property that ABC has degree measure 90, is going to be the circle with diameter AC. And so what this means is we can characterize the circle. So this is the center. The center of the circle would be the midpoint of AC, which is the diameter of the circle. And as you can see, here are the possibilities for where B is. So really what we're trying to do here is we're trying to find the sum of all possible x coordinates of places where the circle with diameter AC hits the x-axis. So that's really what we're trying to find here. So since we have a circle, it's natural to try to find the radius and the center of the circle. So for example, or here we have the center is the midpoint of AC, which comes out as 91, 12. And then another thing that we could find is the radius. And in this case, the radius is the distance from the center to A, or the distance from the center to C. And in either case, this value is the square root of 111 squared plus 10 squared. All right, so now we know some things about the circle. So what we can do now is we can try to find the sum of the x-coordinates. Since this diagram is a bit too far off from the problem, I'm going to redraw it. So really what we have is something like this. So the point -20, 22, 8, and the point 202, 2. Let's say it's around here, and we'll call it C. And what we have for the possibilities of point B are the intersections of the circle with the x-axis. So these two are the points. And we also know the center of the circle, which is the point 91, 12. So let's say this one is k1, 0, and this one is k2, 0. One thing we can notice is that since 91, 12 is the center of the circle, we can drop an altitude to the x-axis, which is a secant because of the circle because it cuts out a chord. And in fact, since we're dropping an altitude from the center of a circle to a chord of the circle, this foot of the altitude splits this chord into 2 equal segments. And so these 2 segments are equal. And then what this means is that this point is k1 plus k2 over 2, the average of the 2, 0. And then we also know that this point has the same x-coordinate as the center of the circle, which is 91, which is 91, 12. So we have k1 plus k2 all over 2 is equal to 91. And so k1 plus k2 is equal to 182. And since we want to find the sum of all possible values of k, this is the final answer, and we're done. So the main idea here is to characterize where the point B could possibly be. And we find out that this point B, since the angle ABC is 90 degrees, this point B has to be on the circle with diameter AC. And then the rest is just constructing some stuff and some simple algebra. So that's it for problem 5. Are there any questions? If not, we can move on to problem 7. All right, there seems to be no questions. I haven't got any yet. So let's move on to the next problem. So in problem 7, we're given 2 equations with 3 variables. And we're asked to find how many ordered triples of integers satisfy these 2 equations. So one thing we could do is we have 2 equations. So we have 3 variables. Is there any way we can reduce the number of variables to 2? So let's try that. We can rewrite the first equation as c equals a plus b minus 12. This way, we can substitute c into the second equation and get rid of this variable c altogether. So we have a squared plus b squared minus c squared is equal to 24. So what we're doing here is we're just substituting the value of c in terms of a and b into the second equation. And then we can expand this. And when you expand it, this is what you get. And now we see an a-b term as well as an a plus b term. So one thing that we might think about is how can we change this equation into something that can be factorized? So we're going to use Simon's favorite factoring trick pretty soon if we can find a way to represent this equation in a nice way. So let's divide out by -12. Sorry, -2, not -12. And then let's add 72 to both sides. So we have this equation. And then we recognize this. We recognize the left-hand side of this equation to be something that we can factor using Simon's favorite factoring trick. Specifically, we can rewrite the left-hand side as a minus 12 times b minus 12. And this is equal to 60. And so now we can notice that for any pair of a minus 12 and b minus 12 that are integers that multiply to 60, we can find exactly one ordered triple ABC that satisfies both equations. So for example, let's say we had a minus 12 is -5 and b minus 12 is -12. This gives us a unique pair, and a unique ordered pair, a comma b, where a is equal to 7 and b equals 0. And then from these two, we can uniquely determine c, which always is an integer, of course, because 7 plus 0 minus 12. These two are integers, and then the sum is also going to be an integer. So we can find a unique value for c as well. So we can do this for any other pair of integers that multiply to 60. And also we can do this for 10 and 6. This would give us 22 and 18. And then a plus b minus 12 would be 28. And this would be another solution. And we can also check that all of these work because, of course, this condition is met. And since this condition is the equation we started with, as long as this triple of numbers satisfies this a minus 12 times b minus 12 equals 60, the second equation should be satisfied as well. So the number of ordered triples of integers is exactly equal to the number of ordered pairs of integers that multiply to 60. And so we can calculate that. So if both a minus 12 and b minus 12 are positive, then we can list all of the possibilities: 160, 230, 320, 415, and so on until 15, 4, 23, 32, and 61. And we can see that the number of ordered pairs in this case is exactly equal to the number of positive integer divisors of 60. And we know that there are 12 of them. So there are 12 in this case. And then the negative case is similar. If both a minus 12 and b minus 12 are negative, we can also find 12 pairs of numbers a minus 12 and b minus 12 that multiply to 60. So the final answer, which is the sum of these two possibilities, is 24. And we're done. So that's problem 7. Are there any questions? All right, so let's move on to problem 9. In problem 9, Natasha is sitting on one of the 35 squares of a 5 by 7 grid of squares. So here we have a 5 by 7. And Wanda wants to walk through every square on the board exactly once, except for the one Natasha is on, starting and ending on any two squares she chooses. So for example, let's say Natasha is over here. Then Wanda can start from any square. For example, she can start from this square, and she can walk all over the place. And from any square, she can only go to an adjacent square. So as you can see here, in this case, she gets stuck if she walks like this. So another way she can walk is by doing this. She also gets stuck. All right, let's start from here. So basically, Wanda can walk sort of any way she wants as long as she goes to an adjacent square every time. So if you do some experimentations, you can guess that there are some squares where if Natasha sits here, there is no way Wanda can traverse the entire board without getting stuck. For example, in this case, she gets stuck again because she does not traverse this square. So we want to find how many squares Natasha can choose to sit on, such that Wanda cannot walk through every square on the board except for the one that Natasha is sitting on. So here we're going to do a trick. So what we're going to do here is we're going to color the board into two colors, somewhat like a chessboard coloring. So let's label these squares as A squares, and they'll appear here, 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 exactly in a chessboard fashion. And let's consider what happens if Natasha sits on a square labeled A, or rather, what happens if Natasha chooses to sit on a square not labeled A. So let's say Natasha sits over here. So since we're traversing 34 squares, all the squares except for the one Natasha is sitting on, in order to traverse the 34 squares, we must have that the number of squares that are labeled A and the number of squares that are not labeled A, these numbers have to be equal because, for example, let's consider this path. And so let's try this. Let's say let's suppose that this thing did traverse all 34 other squares. We notice that in any path, the only place you can go to from a square that's labeled A is a square that is not labeled A. And the only place where you can go to from a square that is not labeled A is a square labeled A. Because for any square labeled A, all four of its neighbors, or all of its neighbors, are not labeled A. And for all squares that are not labeled A, all of its neighbors are labeled A. So we kind of, in our path, we kind of just alternate between squares that are labeled A and squares that are not labeled A. So if we have 34 squares that we're traversing through, that we're traveling through, then there should be the same number of squares labeled A and squares not labeled A in this path. So if we don't consider the square that Natasha chooses to sit on, the number of squares that are labeled A must be equal to the number of squares that are labeled that are not labeled A. But in this case, if Natasha sits here, in the other squares there are, if you count, there are 18 squares labeled A, and there are 16 squares that are not labeled A. (16 squares that are blank). So what this means is that there's no way we can travel through every square on the board exactly once. So if Natasha sits here, Wanda cannot go on her walk. Similarly, if Natasha chooses to go to sit anywhere without an A, let's say here, we would still have 18 squares that are labeled A and 16 squares that are not labeled A. And then Wanda would still not be able to go on her walk. So we notice that these positions that don't have an A on them are places Natasha can sit to stop Wanda from going on her walk. So we know that the answer is at least 17, because there are 17 of these squares. But what happens if Natasha sits on a square labeled with A? Let's say Natasha sits here. And then in this case, we can notice that if you do some experimentation, you can notice that you can always create a path that goes through every other square. So Wanda can go on her walk. For example, if Natasha sits here, Wanda can do this. And if Natasha doesn't sit here, let's say she sits on another square labeled A, Wanda can, let's say she can do this. And it's not too hard to find this type of path that traverses every square on the board for every possibility of Natasha sitting on a square labeled with A. So in fact, if you do enough experimentation, you get a pretty good idea that if Natasha sits on a square labeled A, Wanda will be able to go on her walk. So what that means is the number of squares where Natasha can choose to sit on so that Wanda cannot go on her walk are exactly the squares that are not labeled A. And there are 17 of them. So 17 is the final answer. Okay, so that's this very interesting problem. What we're doing is we're coloring the board in a chessboard fashion, and then we're making observations based on this. All right, a minute for questions. All right, so let's move on to problem 11. So a palindrome is a positive integer, which is the same when read forwards or backwards. We want to find the sum of the two smallest palindromes, which are multiples of 137. So first things first, any positive integer that is a multiple of 137 has to have at least 3 digits. So what that means is we don't need to consider any 2-digit or 1-digit palindromes. We can start with 3-digit palindromes and then work up. And we only need to find the 2 smallest palindromes. So what that means is we can first consider 3-digit numbers, and then 4-digit numbers, and then 5-digit numbers, and so on. Let's start with 3-digit numbers. As for 3 digits, there aren't many 3-digit multiples of 137, so let's just check all of them. We can list out 137, 274, 411, 548, 685, and so on. Next one is 822, and the last one is 959. And we can notice here that these are all not palindromes. These are all not palindromes, but this one is. So now we have our smallest palindrome, which is a multiple of 137. So all that is left to do is to find the second. So to find the second smallest, let's move on to the 4-digit numbers. And now, we can no longer just check every possible 4-digit number as we did here, because there are way more 4-digit numbers that are a multiple of 137. And it also wouldn't be very nice to go through all 4-digit palindromes and check if they're a multiple of 137. So let's try to do something different. 4-digit palindromes look like this. They are always in the form ABBA for some non-zero digit A and another digit B.
But can you flip the B into BAAB?
Oh yeah, you can flip the B into BAAB, but then we can just rewrite that as ABBA since it doesn't really matter what order we make A and B. So for example, if we have the palindrome 7887, we can just write it as A equals 7, B equals 8. So 7887 would just correspond to ABBA. And then for 8778, we can make A equals 8 and B equals 7. Good question. Or good observation, rather. So what can we notice about this number ABBA? We want to check that we want to find A and B such that this number ABBA is a multiple of 137. So one thing we might think of is, what if we can factor this? So is there any way we can factor this? Let's write it out. So we have 1000A plus 100B plus 10B plus A. So 1001A plus 110B. And looking at this, we know that 1001 is divisible by 11, and so is 110. So in fact, we can factor this. We can factor out a multiple of 11. And then we're left with 91a plus 10b. And so now our lives are a lot easier because this makes our lives a lot easier because if this number ABVA is a multiple of 137, 137 cannot go into the 11 because 11 is not a multiple of 137. But 137 can go into this multiple over here, 91a plus 10b. So what that means is that 91a plus 10b is going to be divisible by 137. So let's try some multiples. If this thing is equal to 137, then in order to have b at most 9, since b is a digit, we must have a equals 1. But then if a equals 1, this forces 10b to be equal to 137 minus 91, which is 46. So this is bad. This is impossible. So next we can consider, what if 91a plus 10b is equal to 274? And then in this case, we notice that a has to be equal to 2. No, actually a has to be equal to 3. And then 10b equals 1, which is impossible again. And then we can try 411. We must have a equals 4, and then 10b equals 411 minus 91 times 4, which is not a multiple of 10. So this is bad again. And then you can keep on checking the remaining 3-digit multiples of 137, because this thing has to be at the very most 91 times 9 plus 10 times 9. And that is 9,000. No, sorry, that is 909. So this thing is at most 909. So it has to be a 3-digit number. So in fact, we can try, and then we can see that no other values of a and b work. So if we continue working on this, 548, this forces a equals 6, and then 10b equals 2, which is impossible again. 685 forces a equals 7, and then we would have 10b is equal to 48, which is bad again. And then 822, this forces this forces a equals 9, and 10b equals 3, which is bad. So now we notice that no matter what this is, it's not a multiple of 137, which means this thing is never a multiple of 137. So there are no 4-digit palindromes that are multiples of 137. So now, you might be thinking, we have the first palindrome. We've checked all 4-digit numbers, and none of them are divisible by 137. What next? So I guess the next thing is to not lose hope and continue on to the 5-digit numbers. So you notice that there's not really a nice way to factor the 5-digit palindromes. That's like the way we factored the 4-digit palindromes, because they're of the form A, B, C, B, A. So you might think, let's just try some 5-digit numbers and see if it's possible for it to be a multiple of 137. So let's start with numbers of this form, because these palindromes of this form are the smallest among the 5-digit numbers, since we start with the digit 1. And then we notice that 137, this number, if it's a multiple of 137, it's 137 times something that ends with 3. So we have a number, a multiple of 137, where it's equal to 137 times some number with units digit 3. And then you can notice that this number has to be a 5-digit number. So we can do some estimating to try to find the smallest possible 5-digit number this thing can be. So if, for example, if we estimate 137 times 73, this thing should be around 140 times 70, which is 9,800, which is about 100,000. Sorry, which is about 10,000. So this thing should be very close to 10,000. So let's try to calculate this. If you calculate this, this is where the magic happens. This is equal to exactly 10,001. So in fact, we could have just checked the first 5-digit palindrome, and it would have been a multiple of 137. So we have found our second smallest palindrome that is a multiple of 137. And now we can finish the problem by doing 959 plus 10,001, and this gives a final answer of 10,960. And we're done. All right, so are there any questions? All right, let's move on to problem 13. Okay, this one is kind of like a riddle. So everyone at a math club is either a truth teller, a liar, or a piggybacker. A truth teller always tells the truth, a liar always lies, and a piggybacker will always answer in the style of the previous person who spoke. So what that last one means is if the person before the previous person told the truth, they will follow them. They will also tell the truth. If the person before them lied, they will also lie. And we're also told that if a piggybacker is the first one to talk, they will randomly either tell the truth or lie. So if the piggybacker is the first person to talk, we don't really get much information from what this person says. All right. So we were told that 4 seniors in the math club are interviewed, and here was their conversation. So we have 4 people: Neil, who appears twice in this conversation, and we also have Lucy, Kevin, and Jacob. So there are 4 people. We'll just call them N, L, K, and J. So let's see. Are there any one of these people who are kind of interesting, or any of these lines that are in the conversation that are interesting? So first, one thing that is interesting is that this statement is obviously false. So what this means is that Jacob is definitely not a truth teller. So J is not a truth teller. Not. And then another thing that is interesting is in the 3rd and 4th line, K says, excluding me, there are more truth tellers than liars here. And N says, actually, there are more liars than truth tellers if we exclude K. So these 2 statements cannot both be true, because they're almost opposites. So those are the two interesting things about this conversation. So now let's consider one person. In particular, it's really interesting to consider Neil or N because N says two things, while everyone else only says one thing. So let's do casework on N. So what happens if N is a liar? If N is a liar, then what that means is that we don't really have much that we know so far. Or actually, we do know something. If N is a liar, then L is lying. Or maybe L is not lying, but L is saying it's a false statement. And that does not mean that she is a liar, because it could mean that she is a piggybacker and the previous person is a liar. So in this first case, L is not a truth teller. Okay. So we can divide into two cases, or we can divide into subcases, based on what K is. So one possibility is if K is a truth teller. If K is a truth teller, then that means that since N is a liar and K is a truth teller, because K is a truth teller, excluding K, there are more truth tellers than liars. This is what he said. So since N is a liar, there are at least two other truth tellers. But then that forces both L and J to be truth tellers. And obviously, since J is not a truth teller, this is impossible. So subcase 1 is resolved. It's impossible. Subcase 2 is if K is a piggybacker. Let's just call him the piggy. Okay. So if K is a piggybacker, then there are some more things that we can notice. Okay. So if K is a piggybacker, that means that since N is a liar, that means that there are not two liars among us. So that is one thing that we know. And another thing that we know is that if K is a piggybacker, then L must have said something true. Because there must be more truth tellers than liars in this case. And then if L said something true, this is impossible because we just noted that L cannot be a truth teller. Okay, so the reason we got L said something true is because if there are not an equal number of truth tellers and liars, that would force K to have said something true. But then in order for K to have something true and also be a piggybacker, that would also mean that Lucy, L, must have also said something true. And this is impossible because N is not a piggybacker. N is a liar in this case. So this is another contradiction. And so the last case is if K is a liar.
Why are there two Neils?
Oh, so there are 4 people in this club, and Neil says something twice.
Oh,
Yeah. So the reason we're considering Neil is because Neil said something twice. And so actually what this means is we have a rough sense that we have more information about Neil than any of the 3 other people, because Neil said 2 things, while the other people only said 1 thing. So maybe concerning what Neil is might be our best bet. Yeah, so, all right. And so we're breaking up into cases if Neil is a liar, if Neil is a truth teller, and if Neil is a piggybacker. And then in this first case, we're breaking into more subcases because Neil being a liar is still not too much information that we know. And then if K is a liar, which is our last case, then that would mean that there are the same number of truth tellers and liars. And then if you do some, you can pretty easily see that this is not the case. Because there are not really many cases, there are not really many possibilities for this case, and you can eliminate all of them. Okay, so let's move on to the second case. If Neil is a truth teller, Okay. So if Neil is a truth teller, that means that what Neil said is right. So first, Neil said that there are 2 liars among us. So there are 2 liars among us, among these 4 people. And then also, Neil said that there are more liars than truth tellers if we exclude Kevin. And then we can pretty easily see that it's not too hard to see that the second condition really doesn't give us much. Since Neil is a truth teller, that means that there are two liars among Lucy, Kevin, and Jacob, based on what he said in this first line. So among L, K, J, there are 2 liars. And so who can be a liar here? Since there are 2 liars here, okay, so among L, K, and J, there are exactly 2 liars. And then we can notice that J and L must be liars. Because first of all, J and L both said something false. Neil is not a piggybacker, and 1 plus 1 is not equal to 3. And then we can also notice that Kevin is also not a truth teller. And so, okay, so since Neil is the truth teller, what Kevin said, including me, there are more truth tellers than liars here, this is also false. And we can notice that here, J and L are liars. Because if L is a piggybacker, then that would mean that L said something true, because if L is a piggybacker, she would have followed N, who said something true. And so that would mean that N is really a piggybacker, and that's obviously a contradiction. So L cannot be a piggybacker. And also J can also not be a piggybacker because J also follows N, who said something that is true. So if J is a piggybacker, J would have said something that's true. And J does not say something that's true. So J and L are both not piggybackers. So they must be liars. And then our third person, K, must be a piggybacker, since there are exactly 2 liars. And K said something false. So now we have found, in this case, what everyone is. So we have N is a truth teller. So if we write it in this form, 1 for truth teller, L is a liar, so 3 for liar, K is a piggybacker, so 2 for piggybacker, and J is a liar, so 3 for liar. And this number, M, would just be equal to this in base 4. And then you can calculate this thing to be 123. So this is one possibility for what these people are. But we want to find the sum of all possibilities. So that indicates to us that we're not done yet. There are probably more possibilities. And there's actually one more case in which N is a piggybacker. So we've considered already whether N is a liar, which gives no solutions, N is a truth teller, which gives one possibility for who is what. And then lastly, we have our third possibility, which is if N is a piggybacker. So in this case, what this means is that, firstly, this first line, since N is a piggybacker, this first line doesn't give us any information because if the piggybacker is the first one to talk, he will just randomly either tell the truth or lie. So we're not going to get any information from this line. But then, in our next line, Lucy says that Neil is a piggybacker, and she's right. So what that means is that Lucy said something true. So she cannot be a liar. She can be either a piggybacker or a truth teller. So let's consider both. If Lucy is a piggybacker, that would mean that Neil said something true in the first line. So if Lucy is a piggybacker, she would have followed Neil. But since Lucy said something true, Neil must have also said something true. So there must be 2 liars among them. But then we know that Lucy is a piggybacker and Neil is a piggybacker. So the other 2 people must be liars. So then Neil and Lucy would be piggybackers, and the other 2 people, Kevin and Jacob, would be liars. But then Kevin said something, Kevin lied, and then, so Kevin lied, since we know that if these 2 people are piggybackers, the other 2 are liars. So Neil, in this next step, follows Kevin and lies as well. So now we see that excluding Kevin, there are not more truth tellers than liars, and excluding Kevin, there are not more liars than truth tellers. So in fact, what this means is that the number of liars and the number of truth tellers must be equal. But clearly here we have 2 piggybackers and 2 liars, and no truth tellers. So this gives us a contradiction. The only other possibility is if Lucy is a truth teller. So we just used logic to argue that Lucy must be a truth teller, because if she's a liar, then we get a contradiction. So Lucy is a truth teller. And then we can use the same logic to notice that if Lucy is a truth teller, that would mean that so Lucy said something true, of course, since Neil is a piggybacker. And then whatever Kevin says, Neil would say the same, or this if Kevin says the truth, Neil would also say the truth. If Kevin said something that's false, Neil would also say something that's false, but would also say something true. And in this case, that would mean that there are simultaneously more truth tellers than liars, and there would be more liars than truth tellers. And that's impossible. You cannot have more truth tellers than liars and more liars than truth tellers. So therefore, the number of liars, or therefore, Kevin could not have said the truth. Kevin said something false, that means. And then what that means is that Neil also said something false, because Neil follows Kevin. And that would mean that there are not more truth tellers than liars, and there are not more liars than truth tellers. So the number of liars and the number of truth tellers must be equal. And we know that Lucy is a truth teller, and N is a piggybacker. So in fact, there must be exactly one liar. And this one liar is either Kevin or Jacob. So let's consider it. So if Jacob is a piggybacker, Jacob would have followed Neil, and he would have said something false. And that's exactly what he did. So if Jacob is a piggybacker, then Kevin is a liar and Neil is a piggybacker as well. But more importantly, one thing we can notice is that since Kevin said something right after someone else who said something true, since Lucy is a truth teller, she said something true. And if Kevin is a piggybacker, she would have followed Lucy and said something true, but he didn't. So that means that Kevin is not a piggybacker. In fact, it means that since Kevin said something false, it means that Kevin in this case is a liar. So K is a liar. And then we consider Jacob, which is the last person, J. Since the number of truth tellers and the number of liars are equal, this means that J can only be a piggybacker. So we've found the roles of all four people. N is a piggybacker, J is a piggybacker, L is a truth teller, and K is a liar. So from here, we can find this number NLKJ in base 4, which is 2133. And so we have the answer, or we have M in this case equals 159 once you do the calculations. And then the sum of our two answers is 282. All right, so that's it for problem 13. And right now we're going a bit over time. So if you want to leave, you can leave now. Thanks for joining. If you want to stay, we'll continue going through problem 15, which will be our last problem of the day. Okay, so let's move on to problem 15. Okay, so in problem 15, we have a triangle ABC, and we're told the three lengths. And we also know the circumcircle, gamma of ABC, and also the minor arc midpoints, M, N, and P of the arcs BC, CA, and AB. We're told that K is the area of ABC, L is the area of the intersection of ABC and MNP, and we want to find the ratio L over K. So let's draw a diagram. So here's a diagram. So as you can see here, there are M, N, and P, which are arc points. What that means is that this arc and this arc have equal measure. This arc and this arc have equal measure, and this arc have equal measure. So we want to find the ratio of the area of the intersection of ABC and MNP, which is this area, all over the area of ABC. So one thing we can wonder is there any way we can easily find this area? And it turns out, since we have a really irregularly shaped hexagon, which is the intersection of two triangles, so given this information, there's not really, so far we don't really have a nice way to find the area. So what can we do to this shape to make it easier to find the area? So there are a few things that are interesting about the shape. So firstly, it's not too hard to notice that since okay, so basically what we're doing is we can notice that this segment MP is perpendicular to segment AM. And this is a property of these points that we're considering. And if you do some angle, they sum up to 90 degrees, and then we would have this angle is 90 degrees. And then let's consider this. Since this angle is 90 degrees and these two angles are equal because that this triangle must be isosceles, because in this triangle, the altitude is also the angle bisector. So this triangle is isosceles. So this is equal to this, and similarly, this is equal to this. This is equal to this. And even more that we know is that we can consider these segments as well. So we have this segment and this segment. And so there's more that we can notice. We can also notice that for this quadrilateral right here is actually a rhombus. And this is because if we do some angle chasing, we can actually find out that this, let's mark it with a circle. These two lengths are equal. And this is also part of the configuration in which lies in. So what this means is that this quadrilateral is a rhombus, and that these two are also equal to these two lengths. So we have a rhombus on a rhombus A, this point, I, this point. And similarly, we have a rhombus here and a rhombus here. And another thing we can notice is that since rhombi have parallel opposite sides, these 2 points both lie on the line through I parallel to AB, because in order for these points to be on a vertex of the rhombus, this line has to be parallel to AB, and so does this line. So they're all on the same line. And similarly, we have the same thing for this line and this line. So let's go to the next page where we have a clearer, a more clear diagram, and the rhombi are highlighted. So in this diagram, we have the 3 highlighted rhombi, and also these lines, which are parallel to the sides of the triangle, and they all pass through I. So what we can do here is now we can find if there's an easier way to calculate this ratio. So let's let the non-yellow area equal the non-yellow area in triangle ABC. Let's say this is equal to x. So then that would be the sum of the areas of these 3 triangles. So then we can write our desired area L as the non-yellow regions area plus the area of these 3 regions that are inside this hexagon, but are basically yellow regions. And then we can notice that since these 3 yellow regions are rhombi, we're basically cutting each rhombus in half through one of their diagonals. So in fact, the area of these rhombi that is contained within this hexagon right here is exactly half of the total area of all yellow regions. So we can notice that the total of all yellow regions is the area of ABC minus the non-yellow area. So that is K minus X. So we have this equation. And we can rewrite this in a simpler way. Let's rewrite it like this. And now we can divide through by K. L over K is equal to 1/2 times 1 plus X over K. And so now it suffices to find the ratio X over K. But then one thing we can notice is that, for example, in this triangle, all 3 sides are parallel to the sides of ABC because of the observations we made earlier. So in fact, each of these three triangles are similar to triangle ABC. And we can find the similarity ratio to be this over AC, this over AC, and this over AC. So in fact, the similarity ratios are going to be AP1 over AC, B1B2 over AC, and B2C over AC. So in fact, X over K is equal to the sum of AB1 over AC all squared plus B1B2 over AC all squared plus B2C over AC all squared. So we can rewrite this as this, all squared, and then over AC squared. Or maybe it's nicer to write it as the sum of the square of AB1 over AC, the square of B1, B2 over AC, and the square of B2C over AC. But we'll deal with that later. So now let's try to find AB1 over AC. Because if we can find AB1 over AC, B1, B2 over AC, and B2C over AC, we're done. Because all we need to do is to find this ratio. So let's do that. So okay, sorry, give me a second. I'm going to get a charger. Okay, so let's continue. So what we have here is we want to find AB1 over AC, B1, B2 over AC, and B2C over AC. So how do we find these quantities, these ratios? So firstly, AB1 over AC, let's try to find this. So how can we find this? So now let's use similarity. And this diagram is already a bit cluttered, but we're going to use similarity on this triangle, AYC, and this triangle, B1IC. And we can do this because AB and B1A2 are parallel. So this is equal to the ratio YI over YC, just by proportionality. And then we can notice that YI over IC we can find because we have an angle bisector here, and we can use angle bisector theorem. So let's do that. So YI over IC is equal to AY over AC by angle bisector theorem. And then AY over AC we can calculate as this as AY we can find by angle bisector theorem again. So AY over YB is equal to AC over CB. And then AY plus YB is equal to AB. And then from here we can find that AY is equal to BC over A plus B just by angle bisector theorem. And also we're just saying A is BC, B is CA, and C is AB. So by angle bisector theorem, the calculations are not too bad. You can find that AY is equal to BC over A plus B, and AC is equal to B by definition. So this is just equal to C over A plus B. But if YI over IC is C over A plus B, then YI over YC is just YI over YI plus IC. So that's C over A plus B over C over A plus B plus, or let's write it this way, YI over YI plus IC. So it's YI over IC plus YI over IC plus 1. And this is equal to C over A plus B over A plus B plus C over A plus B. And we can calculate this easily to be C over A plus B plus C. And then we can plug this back in. So 1 squared, another term would be B over A plus B plus C squared. And then the last term would be A over A plus B plus C squared. We calculated the first term, but the other two terms are similar. We can do the same kind of similarity argument. So in fact, this is equal to A squared plus B squared plus C squared all over A plus B plus C all squared. And then we can plug this back into here. But before that, we can also calculate what this is. But I'm going to plug this back in here first. So this is equal to, this is exactly what we want to find. So plugging this back in and then plugging in A, B, and C will finish the problem for us. So let's just plug this in. And this is equal to, once we plug in the values of A, B, and C, which are 11, 13, and 7, we find that this final answer, once we calculate it, is 650 over 961. So that is our final answer. And so L over K is equal to 650 over 961, just by plugging in A, B, and C. And then what we want to find is 650 plus 961, which is equal to 1,611, and we're done. That is the final problem of the day. So I'll wait a bit for questions, and after that, that will be the end of the session. All right, so thank you all for joining. Thank you all, and hope to see you in our next session.